Thank you. Thank you very much indeed, dear Jersey. And thank you everybody for coming to listen the talk. And thank you very much for the series of AMU that you are organizing this time. I would like to say that I'm trying to visualize how methods from set-theoretical topology are important to develop new results in Banach space theory. Okay, if you take a book like the book of Johann Linde-Strauss, which is the chief, okay, is geometric aspects of functional analysis, then in the beginning he says something like the following. After Alexandrov theorem that all Banach spaces of the same density character are homeomorphic, Tarunchik, he said that only topology, because of that, only topology can say few things about Banach spaces. The thing that I'm going to do is to show the contrary, even solving one of the questions that Linde-Strauss left open in 1975, who was unsolved until today. And the way in which I solve the problem is topology. So it's a contradiction to the thing that Linde-Strauss was claiming. The first renorming techniques used in topology was precisely Cabet's proof of the homeomorphism between all separable Banach spaces. To prove that two Banach spaces are separable, then they are homeomorphic, use renorming techniques inside the proof of Cabet's. Now, the thing that happened is that, again, renorming things can be done for Banach spaces of bigger density character. And, for instance, I should say that the Banach space with a Frechet differentiable norm and with separable faces has an equivalent locally uniformly rotum norm. This is, I'm sorry to say, but this is a very deep result. Was a noun if Frechet implies something. Always has been in particular cases. But, for instance, Frechet plus strictly convexity implies locally uniformly rotum norm. This is inside the matters that I'm going to try to translate to the audience. How topological methods lead us to solve problems of geometry of Banach spaces. So let me, this is the contents of the talk. Is solution to problems of Moltot-Troyansky, Valdivia, and myself, which are in the book that you said, these lecture notes. A solution to Haydn, Moltot, and myself questions, which is the things that I was doing with Richard Haydn in Oxford. We wrote a paper for separable compact, and we didn't know about any non-separable case. And we solved, I will say later, the Jordan content and Hausdorff measures are things which help us in our construction. Construction of rule norms slicing with Jordan content is small enough. We will see constructions of rule norms slicing with non-separable in the small norm. We will see construction of rule norms by preserving non-separable faces. This is a very funny thing. Imagine you have a ball for a football match. Okay, the ball of football match is made with pentagons. Pentagons. Okay, what happened in the ball? That if you press a pentagon, you don't go to a new one which is not meeting before. So if you take a ball and you press on one face, and this pressure of the face can be done in such a way that the face doesn't touch any other face distinct of the ones that previous are in the around. So this is perfectly pumped ball. So a perfectly pumped ball is renormed in a locally uniformly convex way. This is completely new result. So solution to Lindenstraub problem, because I will say later, and solution to Richard and Nick question, because this was a problem of 2020, and the solution is that dual rotundity in a dual space, dual rotundity, I have two dual spaces, then this is dual rotund, if and only if this is dual rotund, if they are weak star homeomorphic. So topology, weak star homeomorphism, only topology, preserve dual rotundity, which is a question of the geometrical aspect of the Banach space itself. So this is a solution to Richard in this question, because we did that for C of K, after he did that for aspirant spaces, and I did for any Banach space. So that's the last part. Well, I'm going to celebrate that Michel Talleyrand received the Abel Prize 224, because indeed he was one of the beginners of descriptive set theory inside Banach space theory. Indeed, was a student of Gustave Choquet, and he wrote weekly K-analytic Banach spaces in Annals of Mathematics, 1979. Okay, this paper is a very important paper, not only because it's Annals paper, it's because the contents of the paper. Indeed, related with this, we have, for instance, that Grothendieck proved that the space CP of K for K compact is angelic. Angelic means that all concepts of compactness agree, sequentially, countably, compact, all are the same, compact is the same, all these are the same, and that point in the closure are can be described as limit of sequence. The behavior of the metric space in a non-metric space for compactness is called angelic. I don't know why, but this is the name that they put to this class of spaces. So Grothendieck proved that. I proved that in the case of K-analytic spaces, and I thank a lot Jerzy, because he included these things in his book, and there is a chapter in which they develop this. And even more, we also prove with Cascales that this is angelic, and for the compact open topology, for the topology of uniform convergence on compact sets, the compacts themselves are metrizable. So here we have in point-wise angelic character, and a stronger, and in the strong topology, we have precompact sets are always metrizable. And this is related also with the Burgen-Fremlin diagram, which proves that Ver1 on a Polis space, Ver1 are limit of sequences of functions, continuous functions. So Ver1 is a bigger space than continuous function, a pointwise limit of sequences of continuous functions, and this is a Jellic space for a Polis space. Here we cannot go to an K analytic. We need a Polis. Okay, but the space of functions is bigger. So this is the aim of the very beginning myself in this history. Okay, these are the papers which are related with the things that I wanted to say. Okay, these are the papers. I'm not going to enter. The list is this one. And now just let me tell something about the concept. Norm is said to be locally uniformly rotten if this expression going to 0 implies that xn converges to x. From where it follows this? Remember Hilbert space and the equality in that case, that this 2 plus 2 minus this is equal this to the square. This is in a Hilbert space. This is parallelogram law. So here we are looking for asymptotic behavior of the parallelogram law of a Hilbert space in a general Banach space. We also say that the norm is uniformly rotten, not locally, but all is uniformly rotten whenever this happens with xn and x replaced by another sequence, yn. Okay? And then the limit is also 0. Xn and yn are equivalent sequences. They have the same limit. And this is called uniformly convexity. Okay? This is locally uniform convexity. Well, this Q here is something that I'm going to use. Just remember, is the quadratic form associated to a given norm such that give me the definition of Lure, uniformly Lure, strictly convex, everything. Because strict convexity means that this equals 0 implies x equal y. So strict convexity means Q of xc equals 0 implies x equal y. So these are all the definitions that we need. And then the theorem, the main result. The Banach space, okay, this is written in order to be as general as possible, including dual norms in the case that you are living in a dual space. But in order to understand, forget about this requirement. I just simply think that F is the dual space. And then we are saying that Banach space admits an equivalent Lure norm if and only if they have a sequence of sets such that for every epsilon there is a half space such that X is in this half space in the AP subset, and the slice can be covered with countably many sets of diameter less than epsilon. So let me make a picture here. I have a set A. I have an hyperplane, and I have one side of the hyperplane, this set. So for every epsilon, there exists A's such that diameter of this is smaller than epsilon. This is one condition. The condition that I wrote here is much more general than this one. This one was the condition that we knew because we did this paper in the very beginning with Trojansky and Morteau, in which we characterize Lou renorming as Banach spaces that has this property. But now, here you have AP and X in H AP with diameter less than epsilon. We have this, but not with the requirement that covered by countably many sets of diameter less than epsilon. This is completely new, and this is the statement now. So this was in the history, the past. Now I say, if I put here balls, countably many, of diameter less than epsilon, or epsilon, then I cover all the slides. I eat the slides with countably many balls of diameter less than epsilon. The past was I eat the slice with a single ball of diameter less than epsilon. This was the very beginning of the history about Lou renormings of Banach spaces inside descriptive set theory. Okay, so now the renorming can be achieved every time we have this is far away, epsilon, far away, epsilon, far away from a separable piece. Every time that you cover with countably many, or even every time the distance to some separable piece of the space is less than epsilon. It's the same. Okay, so, and this is.
I have a question. So in this renorming, the norm is equivalent, and then the constant depends on.
No, this is if and only if.
But renorming, then the constant which appear in equivalence to the original.
The constant for the renorming.
Yes.
This I cannot control.
Okay.
Okay. So if it's 1 plus epsilon, 1 minus epsilon, okay, this I cannot control.
Oh, okay.
But this is a very good question. Okay. Because other things. But anyway, this is the theorem. Okay, this is the theorem. This is the main result. This result completely resolves 4 problems asked by Morteau, Trojansky, Valdivia, and myself. It generalized Trojansky's fundamental result. You can see it in the chapter 6 of the Virgo de Hitler book. Morteau, Trojansky, and myself theorem in Lou renormings also is generalized. I said it before. Lancien and Raja's approach is also generalized, as well as Garcia, Oncina, Trojansky, and myself, where finite covers were considered too. We consider, before arriving to that, we consider Kuratowski index. Kuratowski index is a measure of non-compactness, so can be covered by finitely many sets of diameter less than epsilon. We did that. We did that in the way of proving this result. Okay. A has an equivalent. Okay, I always say lower semi-continuous, blah blah blah. But as I told before, forget about that. This is technical thing in order to have dual norms. If and only if there is another one with separable denting faces. So the only thing that I need is in the football ball, the faces are the pentagon. This must be separable pentagons and dented. That means if you press down it, you take the complementary, you make the convex hull of the complementary. You don't teach, you don't take any point of the phase. This is a denting phase. It's a denting point from radon encoding property as a denting point, and now with the phase. So these are a very precise answer to read the Strauss problem for Lur norms. Well, Banach spaces C of K, where K is Rosenthal compacta. Rosenthal compacta are compact sets of the first Bell class of functions on a Polish space. So this is another typical space in which we live almost half of the life. This is Bell1 functions on a Polish space. So if the Bell1 functions on the Polish space are formed with functions with at most countably many discontinuity points, then the space is locally uniformly Rotten renormable, and this answers a question of Haydn, Molto, and myself, because we wrote a paper in which we proved this for separable compact. For non-separable compact, we wrote the problem because we didn't know. So this is also solution to this problem. So these are the solutions to the problems that I presented, and it's not written here the one that I said of Richard Smith that I also solved in the context. Okay, which is the topology natural definition that I need in order to achieve all this? Is the network business. Network business. A network is a family of subsets that behaves as a basis of neighborhoods of a point, but they are not required to be open. They are required just to be sets. Okay? So a network, again, is the same as a neighborhood basis of every point, but the sets are not necessary to be open. So this is the concept of network. A central result in the theory is the following. We have enormous space and enormous, okay, as always, admits a Lur norm if and only if there is a sequence of sets such that every point belonging in one of the pieces has diameter less than epsilon. Why I said now network? Because the sets, these sets, all these sets, the slice and the thing that half space mean, is a family of sets which by the very definition is a network of the norm topology. It's a network of the norm topology. So in a very natural way, I have a network of the norm topology just with these requirements. So the concept is there. Another definition which is inside the matter is that the Jordan content. Jordan content means I need to have measures. I need to have measures of size of these sets, of this slice, of this slice, of this slice, and the one kind of measure is Jordan content. You can play with this Jordan content instead of diameter. You can always use a Hausdorff measure of the set and say that the Hausdorff measure must be finite. This is another thing which you can play with this definition of Hausdorff dimensional measure. You can even work with the metric measure, which is the one given the general definition of Hausdorff measure, alpha dimensional Hausdorff measure. So we can take these sets in order to have this with finite alpha Hausdorff measure. It's enough. It's enough also to have zero measure, zero alpha outdoor measure. This is always the same. And let me just do the following. Okay, I will leave later. I don't. Okay, these are measures of size of these things, and all of them are included in the theorem because to be epsilon distance of a separable piece is much more general. Because every space with outdoor measure finite is separable. So it's separability distance epsilon is the more general thing that we are going to have. How we prove these results? How we prove these results? With the things that you know, open localization theorem. The open localization theorem is the following. Imagine that you have a set, a piece of bread, and you have slices. With a knife, you have been taking slices. Okay, slicing. You break with a knife. Then the localization theorem says conditions in order to describe with a norm that if you take 1 point x0 in one of the pieces, then there is a norm such that the null condition on it is going to imply that the elements of the sequence are going to be in the same piece. So this is why I said open localization theorem. You find a family of closed convex sets, which are the half spaces, the closed half spaces, okay? Theta y are closed half spaces. Then there is an equivalent lower semi-continuous norm associated to this situation, such that if 1 point x is in one of the pieces, and xn is a sequence verifying the null condition with the Q, remember Q, the quadratic form, then there is a sequence of indexes such that x belongs to these sets 2, and if the xn are in A, then they always belong to the same place. So x and xn are going to be in the same place. And this is the thing that I need, because if the place is a place which is covered by a finite number of balls of radius epsilon, at the end I have infinitely many of the sets of the sequence that is less than epsilon for max 0. So this is the first approach. And in the second approach, additionally, we will start have the following in case only the x0 is there. If the xn are not in A, if the xn are not in A, then I can make a convex hull of the piece radius epsilon, and x and xn will be not far from there. So delta is for every delta there exists. So I have this delta, and the xn is here. Maybe it's not in the set, but it's there. It's there. Maybe it's not in the set, but it's here. So this is very important, because if this is a small, convex hull is a small. If this is a small, plus delta ball is a small, and the closure is a small. So it's the thing that you need. is the thing that you need to approximate xn and x0. So, and this is the picture. So, this is the theorem. The delta combis network are equivalent that one space has a lower semi-continuous equivalent locally uniformly brought to a Lur norm. There is a sequence of sets, sequence of ball centers at 0, having rational radius, and H denotes the family of open half spaces, and the family of the intersection of open half spaces with the sets again is a network for the norm topology. Or you can describe the network as in 3, which is difference of closed convex sets. So here you are saying that there is a network of the norm topology which is formed by difference of closed convex sets, where one of the elements of the difference is in a sequence of sets that we have from the very beginning. There is a sequence of subsets that blah, blah, blah is the same. That's the convex networking. Now read the question. The question is written as follows. It is easily verified that every separable Banach space has an strictly convex norm. The same is true for a general weakly compactly generated space. On the other hand, it was shown by Day and myself and Lindenstrauss that there exists Banach space which do not have an equivalent strictly convex norm. Some conjectures concerning a possible answer to the question were shown to be false by Dassel and Lindenstrauss. This result shows that even for COK spaces, it seems to be a delicate and presumably difficult question to decide under which conditions there exists an equivalent strictly convex norm. Okay, this is the question. So, characterize a strictly convexity in a way that could be handleable. This is the question of Lindenstrauss, and this is the definition in order to solve the question. The strict convexity is a property of separation. So we have the definition is here. We have families of sets W sub n such that any 2 points which are different, there is one of these families such that X is in the sets in some set of the family and Y is not there, or the reverse. Okay, so it's a separation property as it is written down there. We call this property star because writing the paper with Richard Smith and Stanimir Trojansky, okay, we didn't like to say that is Orihuela's, but what's my invention? This I'm saying that because nobody says so. They are Jersey. This is the very beginning of the history. Means that we introduced this property, and I did it. So this is the star property for a family of subsets. The star are all the elements of the family. This is in order to understand the definition, and we can also say that a family of functions separate points in the corresponding, let me say, open sets, if they are continuous. These sets separates the family. So I can give the T0 star separation property either with functions, either with sets. And this is the thing that I'm going to use because the strict convexity renorming theorem says that a Banach space with an admits an equivalent strictly convex norm if and only if there are a family of quasi-convex functions that T0 star separates the point. A quasi-convex function is a convex function is also true. Take a convex function and truncate it. This is a quasi-convex function. Preimage of 0 or alpha less or equal is a convex set. This is the definition of quasi-convex. You can write there convex without any problem. Define a system that T star 0 separates the points. So this is the characterization. Okay. So what happened and why we are touching? Sorry. I'm very sorry for that. Okay. Okay. So now, Nagata-Smirnov theorem, metrization theorem says that a topological space is metrizeable if and only if you have a sigma discrete basis. This is for the norm topology. To have a Luru norm is equivalent to have a sigma discrete basis, which is also sigma slightly isolated. Sigma slightly isolated means that I have a family of subsets an isolated sigma means that if you take one point in one of the set, there is half space that doesn't touch any other set in the family. Is discreteness with half space, relatively discreteness with the width topology, but even more with half spaces, half semi-spaces. Okay, so this is the theorem of Nagata-Smirnov meeting the weak Luru norming, or in dual spaces. In dual spaces, I can even take not this, but a quick open set. The intersection of an finite number of slices. This is dual Luru. It's the same. So it's a complete characterization in topological terms of the matter. Slicing with finite half-door measure sets. This is something that I told you before, and it's not necessary to read. I said before that the same results are valid with the half-door measure. And here is the result written with null half-door measure. Null half-door measure means that the slice is as small as this. This is null half-door measure. So it's another way of measure, but all of them are included in these things, which is that the slice have a separable piece epsilon apart from. That the slice has a separable space epsilon apart. That's the main result. Okay, so Luru is equivalent to this, and as a corollary, a Banach space has a lower semi-continuous Luru norm if and only if there is another one with separable denting faces. This I said before too. The proofs I'm not going to enter. Okay, in the proofs. The proofs are working with all the information in order to be able to control the norm. The main tool for the proofs is a lemma known as the Bill master lemma. The Bill master lemma is in the book of, it's not final chapter, but the chapter in which is written Luru normings in the book of Fiedler, Banach, Fiedler, Godefroy, and the Bill. There is a big lemma that everybody knows as the Bill master lemma. For instance, Richard Haydn told me that when he recited the lemma, just put on the table because he thought it was not a good one. And after working, remember one day that something of the situation that was presented in the lemma appeared for him. Then he began to write all these trees, all these counterexamples about renorming. And this, the very beginning was the Bill master lemma. The Bill is another of the guys that we was yesterday talking about. Okay, so this is the lemma, And the theorem, a normal space has a Lure norm if and only if can be decomposed in pieces for every epsilon, such that in every one of the pieces there are Kuratowski index less than epsilon. This is one of the theorems. This is true not only with Kuratowski index, but with the separability index that I said before. Okay. Again, the lemma. Again, the theorem. Banner space has a locally uniformly rotor norm if and only if every point in the sphere has a slice that can be covered with comfortably many sets of diameter less than epsilon. So even I can make the proof of the statement in the given Banner space, in the given Banner space, in the given sphere, I have this is the sphere of the Banner space. This is the ball. Every point here has a slice that can be covered by comfortably many sets of diameter less than epsilon. This is the thing that is said. So denting points are points in which diameter is less than epsilon. This is much more because it's modulus separability. So you have this kind of result also in order how to glue separable pieces, but I prefer not to read this one. I prefer just to go directly to the separable plus sigma slightly isolated faces. If you have a normal space and you have a family of separable faces of its unit ball, which is countable union of slightly isolated sets, then the norm admits an equivalent locally uniformly rotor norm at every point of the union. So this is also a local theorem. It's also a local theorem. I can describe sets in which you can norm to be Lure. A Banner space admits an equivalent locally uniform rotor norm on the union of family of compact separable and sigma compact faces. Every time that each subfamily is weakly relatively discrete. So this is relatively discrete in the weak topology. So this is another condition of the same kind and natural. Let me describe now the press down on the ball that I said before. So pressing down the ball. A Banner space with an you have a locally uniformly rotor norm whenever you have points in the union of faces separable such that they are disjoint with this definition of disjoint. If I press a little bit A minus delta and press a little bit B minus delta, A and B are faces, they don't touch. Okay, so this is the theorem of pressing down the ball in order to obtain locally uniformly rotor norm. This is completely new result. What about descriptive spaces? The descriptive spaces that appears when one study the relationship between renormability and fragmentability, the work of Jane, Rogers, and Namioka. From Lure to sigma fragmentability in the middle are descriptive spaces. For these descriptive spaces, you have a family of compact and separable faces, such that every one of the families Fn is norm relatively discrete. You can construct a locally uniformly rotor norm in every one of these faces. This is again renorming for descriptive Banner spaces, and as a corollary, a normal space descriptive, a Banach space which is descriptive, admits an equivalent strictly convex norm. It also has another one which is Lure on a norm-dense subset. So in any descriptive space, as well as you have a strict convexity, you have Lure on a dense subset. This is also, I think, an important result. Anyway, the theorem that answers Lindenstrauss is this one. Let it be a normal space with a norm in subspace F. Let me, in that case, fix F because it's important. It admits an equivalent lower semi-continuous rotor norm if and only if there is another one with weakly caused non-separable phases. So this is, I'm pretty sure that this was the answer to the question that I said before, because he asked for conditions for strict convexity, characterize strict convexity, because I don't have this, I don't have this, I don't know this, I don't know this. I know separable, I know. So the separable, where they are? In the faces. If you are able to glue a ball with separable pieces, with separable faces, you have a strict convexity. If and only if. That's Lindenstraus question. That's the solution to Lindenstraus question. 1975. Well, this is the theorem that is necessary to write down in order to achieve it. It's exactly the same situation as before, and now the family of half spaces are separable and only separable, and then from the condition of strict convexity you have x equal y. So this is the theorem that proves and give the answer to Lindenstraus. And now to finish, let me ask the answer to the problem of Richard Smith. Richard Smith wrote with Trojansky and myself this theorem for C of K star, where K is compact, scattering, because of the situation. Later, he did it for Asplund spaces. He proved it, 2020. But in general was unknown, and in general is this one. E star a dual Banach space, E star admits a dual equivalent norm if and only if the unit ball has the property star, this T0 star, with a weak star policy. Nothing of half spaces here. It's not necessary. You can get rid of the half spaces. It's a purely topological argument. It's a purely topological statement. So as a corollary, if we have two dual spaces, weak star homeomorphism preserves dual strict convexity, far of the thinking of Lindenstraus. And this is the way I'm closing. Before, let me historical comments of this matter. The historical comments are the following. This Lure renorming implies gathered renorming, implied descriptive spaces, implied weakly check analytic. Weakly check analytic is the notion that a space can be looked at the bidual, construct a Suslin scheme in the bidual with open and closed subsets, such that the Suslin result, the Suslin scheme gives the space. This is weakly check analytic. K analytic is Suslin scheme with closed sets. Suslin scheme with closed or open set is check analytic. And check analytic implies the class of sigma fragmentary space of Jane Rogers and Namioka. So here the beginning is Peter Enflo and Pichier with the renorming uniformly rotundity. Later Jane, Namioka, Rogers, as I said. Later, you can send a frolic. By the way, I have anecdote with Frolic. Frolic was, for me, a wonderful man that went to Murcia because we invited him, and he realized there that he was excited when he had a look to the theorem of angelicity. He was very excited. You did it. You did it. It was the only thing that he was saying all the time. You did it. He invited me to the winter school. Well, in these winter schools, you know, everybody has a room with somebody else. I spent the night with Frolic. So he invited me and spent the night with him. And for me, I was astonished. Nothing will happen. That was the result. Okay, what was the result? Well, Havala, Hansel, Holisky, Peter Hayek, Jessica Coleman, sorry, because the W they are, Haydn and Smith, Trojansky and Kenderov also made contributions to the matter, the Virgo, the Fral, Ancien, Václav Schindler, Fabian Kubis, Calenda, Argyros, Mercourakis, Negropontis, and Van der Brecht. All of them have been contributions to the history, Ribarska and Moores, and later all these Spanish guys that also made contributions to the matter. So this is the historical context of our research, and the main question that remains are: does every binary space with Radon encoding property has an equivalent locally uniformly rotor norm? I think the answer is yes, but it's necessary to prove that every binary space has the so-called weakly theta refinability property, which is a covering property. You can have a look on Grunheim's paper in Handbook of Set-Theoretic Topology, and there is the definition of weakly theta refinability. If the binary space is hereditarily weakly theta refinable, the answer is going to be yes. But nobody knows an example of a binary space which is not weakly theta refinable hereditarily. So it's a property that is necessary to investigate. And the next one is a Frechet differentiable implies blue renorming. This is Godefroy called many times that his dream is this one, this problem. Okay, this dream, I already know density character omega 1. This is true. And it's also true when the phases are separable. It's also true. So Frechet plus rotundity is true, of course. But in full generality, I don't know. And I think that from density character omega 1 to the others, I need the separability of the phases. And probably it's not possible to get rid of it. But anyway, this is the dream of Godefroy. It's also my dream, of course, because I follow him. And that's all what I wanted to say. Thank you very much.